Hey guys, now that we've learned the radical tools that we need for Chapter 9 and 9.1, we can move on to starting to solve quadratic equations using different techniques. So make sure you use graph paper for today's notes and homework because obviously we're going to be solving quadratic equations by graphing. So take a moment to set up your note sheet with the section, the date, and the I can statement, and then resume as soon as you are ready. All right, so just to recap, there's 5 methods for solving quadratic equations. We spent most, if not all of chapter 7 solving quadratic equations by factoring. That was one method. In this chapter, we're going to learn the other 4. And in 9.2, we're going to focus on solving quadratic equations by graphing. So just to give you a sense of where we're headed, you can see all 5 solving techniques here. So we've learned how to solve quadratic equations by graphing before. We actually did this in 8.5 at the end of chapter 7 when we learned how to solve an equation like x squared plus 2x equals 3 by graphing. So in section 8.5, to solve this problem, we would have set it equal to 0. So x squared plus 2x minus 3 equals 0. And then we would factor it using sum and product, where the sum was 2 and the product was negative 3. So our factors would have been x plus 3 times x minus 1. And so then our x-intercepts would be x equals negative 3 and x equals 1. And so graphically we would have plotted negative 3 and positive 1. And then that told us that our axis of symmetry was at negative 1. So we would plug negative 1 into the original expression. So we would have negative 1 squared plus 2 times negative 1 minus 3 to get our vertex, which would be 1 minus 2 minus 3, which is negative 4. So this is strictly a review, right, from chapter 8. But I wanted to go over this because this is one of 2 methods that we can use to solve quadratic equations by graphing. However, there's a second method. And this second method is sometimes a little bit more illuminating for certain situations. So method 2 is instead of setting it equal to 0, so for method 1, our general strategy is to set equal to 0. For method 2, instead, our goal is to isolate x squared. In other words, we want to have x squared all by itself. So for this, we would subtract 2x from both sides. So we would have x squared equals negative 2x plus 3. And then all we need to do, we've done this before a few times this year, is we're going to graph each one of these separately. We're going to graph y equals x squared, and we're also going to graph y equals negative 2x plus 3. And where they cross will be our solutions. So if we first graph y equals x squared, and the only thing with this is we have to be pretty precise. So we have a point at 1, 1, and 2, 4, and 3, 9. And same thing on the other side. So this is our y equals x squared graph. And then our y equals negative 2x plus 3. So this is a linear function, so we're going way back, right? We have a y-intercept of 3. And we're going down to over 1 and up to over 1 as well. And so that gives us our linear function. And where they intersect, the x-coordinates are our solutions. And you can see here that we intersect at x equals negative 3 and positive 1. So either method gives us the same answers. They're just 2 very different approaches to the same problem. And one of the advantages of the second method is it gives us a little more flexibility in solving some additional problems. And we're going to look at that in a second here. So two methods to solve the same type of problem. So let's look at two more examples, and I want to use the second method here for this. So the first one, we're going to have x squared plus 9 equals 6x. We're going to isolate x squared. X squared equals 6x minus 9. And then we're going to graph y equals x squared, and we'll graph y equals 6x minus 9. And when we do that, we're going to put in our points here. So 1, 1, 2, 4, 3, 9. So I'm going to put in my y equals x squared curve. And I'm also going to put in 6x minus 9. So we're going to use a slope of 6, so we go up 6 over 1. And draw in our linear function here. And the reason I wanted to show you this example was because this is an example of one where there's only one intersection point. And that one intersection point occurs at x equals 3. And we've seen this a few times, right, this year, where if we only have one intersection point, that means if we were to graph y equals x squared minus 6x plus 9, in other words, if we had set it equal to 0, that one intersection point would have been the only x-intercept and also the vertex. So that x equals 3, that would represent our vertex. Now, the second example here is really the one that demonstrates why method 2 can be really nice. So for this example, we're already we have x squared isolated, so I'm going to graph y equals x squared, just like before. And then I'm also going to graph y equals 3x minus 3. So we'll put our y-intercept at negative 3, and we're going to use our slope of positive 3. And for this problem, we kind of come to an interesting conclusion here, which is that these never intersect, right? So our solution here is actually that there are no solutions. But we couldn't really have known that with method 1, because if we had used method 1, we would have come up with a situation, so we would have had x squared minus 3x plus 3 equals 0. So our sum would be negative 3 and our product would be positive 3. And at this point, you would have gotten stuck. You would have said, well, there's no two numbers that multiply to positive 3 but add to negative 3. The problem is we don't know if this is because there's no solution, or maybe there are solutions, it's just not factorable. And there's no way really to be able to tell the difference between those two things without learning some new solving techniques. However, if you use method 2, you can see visually that there's actually no solutions. So this is important because this is one place where method 2 is a little bit more useful than method 1. Method 1 is what we learned back in chapter 8. With this new method, though, we can actually see a little bit more information. So let's look at another example here so I can demonstrate even a little more to you what I'm talking about. So the graph of f of x equals x squared plus 4x plus 1 is shown below. What I want you guys to notice here is look at this graph. X squared plus 4x plus 1, our sum is 4 and our product is 1. There are definitely not two numbers that multiply to 1 but add to 4. So you would have said not factorable, right? But notice that this graph clearly has solutions because we've got two x-intercepts. They're just not whole numbers. And so this is important because this shows the difference between not factorable, which still can have solutions, and no solutions, like we saw in our last example, because they actually don't cross. So the difference here is pretty clear. If we graph, I want to graph each of these so you can see how these look. So if we were to graph x squared, y equals x squared minus 3x plus 3. In other words, I'm graphing this one, just set equal to 0. If I graph this, you can see right away why it has no solutions. It's because the parabola is upward facing, but above the x-axis, so it never crosses the x-axis. It has no x-intercepts. So this is an example of one that really does have no solutions. But if we go to our next example here, you can see that there clearly are solutions, but it's not factorable. Which is sort of a limitation of our earlier method. We don't know if something is not factorable or if it truly has no solutions. Now, we can use our calculator to approximate the zeros of f to the nearest tenth. And this is something you'll do for certain problems on your homework where it says approximate or asks you to find decimal solutions. You can use your calculator for those. So this would be x squared plus 4x plus 1. And if I graph this one, I'm going to see the same picture I see in the graph. Our calculator has a tool to be able to find the zeros, the x-intercepts. Remember that they're called zeros because y is 0 on the x-axis. So I can go to second calculate, go down to number 2, the 0 one, and it's going to ask me left bound first. So I go to the left of the one I want, hit enter. I go to the right of the one I want and hit enter, and then I guess. So my first 0 would be negative 2, and we want to approximate to the nearest tenth. So my first 0 would be x equals negative 0.3. And then my second 0, I have to do the process again. So second calculate, go down to number 2, and then this time we need to tell the calculator to look at the other one. So we go to the left of the other one, we hit enter. We go to the right of the other one, hit enter, and then we guess. And this time we get negative 3.7. So our two zeros would be x equals negative 0.3 and x equals negative 3.7. Notice that although it was not factorable, we do have solutions. And in our future lessons, we're going to learn how to find these solutions algebraically as well. So let's look at a final example here. So this is sort of more of a word problem scenario. So imagine a football player punts a football from a height of 2 feet above the ground and an initial upward velocity of 75 feet per second. We can model that with the function h equals negative 16t squared plus 75t plus 2, where that represents the height of the ball after t seconds. And again, you can see gravity pulling it down. So in football, they care a lot about something called hang time, which is the amount of time that the ball is in the air from the time it's kicked until the time it lands. Because the longer the hang time, the better, because it allows the players on the football teams, on the punter's team, to try to get really close to the player on the other team who's going to catch the football. So they want the ball to hang in the air a really long time. So our goal is to use our calculator to determine the hang time for this punter. So we're going to use our calculator and graph this expression. So y equals negative 16 x squared, obviously there's no t, but we'll use x instead, plus 75x plus 2. Now, if I hit graph here, I don't really see very much, right? I see a bit of my expression, but not all of it. But what I do notice is a couple things here. I can find the time at which the ball hits the ground. So I can go to second calculate. And you know what, before I do that, actually, I'm going to change my window a little bit. just to make this show up a little better. So let's go from -1 to 6 instead. And I'm going to raise the height as well to say like 50, just to see if we can see this punt a little bit better. All right, so that shows the punt a little better, and I could make the window even bigger, but I don't need to. Our goal is just to figure out where that 0 is. So I'm going to go to second calculate 0, and it's going to ask me my left bound. And I need to find my thing, because right now it's way up high somewhere. But if I move closer, I can, oh, there it is. So there's my left bound, and then I'm going to scroll down for my right bound, and then I'll guess. And that gives me my the time at which the ball hits the ground. X equals 4.71 seconds. So time equals 4.71 seconds. So obviously the ball left the punter's foot at time 0. It touched the ground at time 4.71 seconds. So that time was the amount of time the ball was in the air. That was the hang time for that football. So that brings us to the end of this lesson video. For some of the homework, you'll be using your calculator to approximate solutions. And that's particularly true for word problems as well. But for much of the homework, you're going to be doing it graphically by hand. And I want you to be trying method 2, because that one will give you answers even in situations where method 1 won't work because the problem isn't factorable. So I want you to be practicing method 2 for this homework assignment. So give the homework a try and let me know if you have any questions.